Boa noite, comunidade SPE Brasil e SPE Internacional, né? A gente está hoje aqui abrindo o Tech Tuesday, tá? E eu tenho aqui o prazer de fazer a abertura para vocês. Meu nome é José Sérgio, sou diretor de eventos da SPE Brasil. E antes da gente dar início à nossa palestra, uma palestra internacional que a gente está trazendo para vocês, a gente vai falar um pouquinho, né, das novidades, dos updates que a gente tem aqui na nossa sessão, tá bom? Então, no próximo slide, a gente quer divulgar aqui para vocês o flowchart de número 21, né, que vai falar sobre desafios de flow assurance, com foco aí em CO2-rich fluids em CCS applications. Então, um tema bem atual, né, relacionado à captura de carbono, e a gente vai contar com a participação do João Carneiro, né, que ele trabalha na ISDB Flowtech, o Randy Rodrigues, Lead Flow Assurance, consultor da Wood, e o Eduardo Luna Ortiz, né, que é diretor técnico da PACE CCS. Então, uma apresentação bem atual, um tema bastante importante, né, e a gente gostaria da participação, né, da nossa comunidade. Ok? Bom, no próximo slide, a gente gostaria de divulgar aqui a todos, né, que o ano que vem, o ano de 2024, é um ano muito importante, né, para a comunidade do SPE. É o ano no qual o SPE-ATCE, o importante evento da nossa comunidade, faz 100 anos. Tá? E o tema, né, no ano de 2024, vai ser Powering the Future of Energy, with a Century of Innovation. Então, é um evento em celebração aos 100 anos desse importante evento da indústria, né, no mundo. Tá? Então, é importante saber, né, que a chamada para papers, né, artigos técnicos, está aberta. Tá? Então, a gente gostaria de estimular a comunidade, né, a submeter, né, seus resumos, seus abstracts, né, para contribuir nessa edição, que é uma edição muito importante, né, para a SPE Internacional, né, o ATCE 2024. Tá bom? Falando agora um pouco da nossa Tech Tuesday, né, a gente está preparando, né, uma série de palestras, e eu tenho a honra de trazer para vocês aqui no dia 12 de dezembro, a gente vai ter a Ruth Thomas, né, falando de Subsurface Basis of Design, the most important part of weather commissioning. Tema também bem atual, importante, descomissionamento. A gente está trazendo aqui uma expert da indústria, né, para falar um pouco da experiência, né, da atividade de descomissionamento, aí, mundo afora. Né? Então, a gente pode ter a oportunidade de aprender e se atualizar nesse tema tão importante, né, da atualidade. Ok? Próximo slide. Em termos de eventos, em novembro desse ano, ainda esse mês, né, dia 28 e 29, a gente vai ter o SPE Brasil Subsea Symposium. Né? Eu convido vocês a acessarem o site, né, da SPE Brasil, e participarem desse importante evento, tá, que vai falar sobre aspectos de tecnologia subsea, né, aqui no nosso país. Okay? Um outro evento muito importante, né, ainda esse ano é o SPE Awards. O SPE Awards é um evento que tem o objetivo, né, de premiar, né, as pessoas que contribuem bastante, né, na nossa indústria, nos diversos temas, nas diversas disciplinas, né, aquelas pessoas que tiveram destaque, né, no ano de 2023. Então, a gente está preparando um evento muito bacana. A chamada para indicação, né, dos premiados já está aberta. Ela vai fechar no dia 25 de novembro. Então, vocês já devem, os membros aqui da SPE já devem ter recebido, né, esse e-mail, e eu convido todos vocês a acessarem e indicarem, né, seus colegas, né, que vocês entendem que se destacaram e que contribuíram bastante, né, para a indústria nesse ano de 2023. Ok? Por último, aqui, mas não menos importante, né, esse momento é um momento especial aqui também para a SPE Brasil. A gente gostaria de não só de anunciar, né, mas de parabenizar o Carlos Alberto Pedroso, nosso querido presidente da SPE Brasil, que agora ele vai atuar como diretor regional da SPE, né, região Latin America e Caribbean. Então, a gente trouxe aqui o Pedroso para dar umas palavras para a gente. Boa noite, Pedroso, tudo bem?
Boa noite, Sérgio. Muito obrigado pela introdução aí, obrigado pela parabenização. É a minha primeira aparição pública como o diretor regional da América Latina e Caribe. E não tinha um momento mais adequado do que uma Tech Tuesday, porque durante quase 2 anos a Tech Tuesday fez parte da minha vida. Toda terça-feira eu estava aqui abrindo as Tech Tuesday, e, sem dúvida, esse reconhecimento a nível regional, ele é fruto do trabalho da SPE Brasil. A SPE Brasil realmente atingiu um patamar assim de reconhecimento dentro da SPE e fora também, né, por toda a indústria, e, obviamente, é o fruto do trabalho de toda a diretoria, todos os membros da SPE que têm participado dos comitês técnicos, que têm dividido seus conhecimentos, compartilhado seus conhecimentos através das terças técnicas, através dos flowchats que estão aí, através dos Energy Talks, de toda a forma, né, do trabalho que tem sido feito para o compartilhamento de conhecimento. E foi exatamente toda essa atividade que chamou a atenção da comunidade internacional e me guindou, então, para essa posição de diretor regional. Então, eu tenho muito a agradecer à SPE Brasil, a todos vocês que têm participado. Deixa eu aproveitar, e nesse momento eu sempre agradeço as pessoas que nos ajudam, e eu gostaria de agradecer ao Ian e à Amanda, que estão aqui, e também ao Sérgio, né, que está organizando, e ao Danilo Colombo, ao Clement, ao Clement Julan, e também ao Pierre Eduardo, da nossa diretoria, que tem trabalhado na organização, que trabalhou na organização desse evento. Então, um grande agradecimento a todos, um agradecimento a todos que nos acompanham, é para isso que a gente faz esses eventos, né? Exatamente para o público. Então, agradeço muito a todos por esse apoio e espero que eu consiga desenvolver um bom trabalho também na América Latina e Caribe. E com isso, então, agradecendo mais uma vez a Amanda, eu gostaria de chamá-la, então, para a tela, para ela continuar, então, encaminhando esse evento. Amanda, seja bem-vinda, a tela é sua.
Obrigada, Pedroso. Bom, vou começar falando inglês aqui, né? Good evening, people. I hope everyone is well. My name is Amanda Kortkamp. I'm a petroleum engineer student at UFRJ and SPE Brazil section. So I would also like to invite you to participate in the SPE opportunities on November 28th, which will be broadcast here on our YouTube channel, where Halliburton will talk about their internship program. And before we start Clemon's presentation, I would like to call on Danilo Colombo, who is a mechatronic and petroleum engineer who currently has a position as a technical advisor at Petrobras for reliability and risk assessment. He holds a doctorate degree in reliability engineer and a master's degree in well integrity. He also holds an MBA in investment management, and he is certified as a reliability consultant. He has been coordinating R&D project at Petrobras R&D Center, SEMPS, for the last decade together with universities and research institutes. And during this time, published around 100 papers and book chapters. His current research interests include machine learning, data analytics, and digital transformation for well integrity management and risk analysis. He is currently coordinating the Brazil booklet of best practice for risk assessment for wells. He's a member of SPE and Abrisco, Brazilian Association of Risk Analysis, Reliability, and Process Safety.
Hi, Amanda. Thanks for the kind introduction. Hello and good evening for the participants on YouTube. I hope you all enjoy today's presentation. We all know that well integrity is a crucial activity in the oil and gas industry. But nowadays, it goes beyond being very important for geothermal wells, CO2 storage wells, and so on. And we crave more computational tools that can provide important insights on support our management, our decision-making from the design of the wells to its operation and finally planning and abandonment. Today, Dr. Clement Jolan from Net Zero Geosystems will honor us with the presentation called the Hyperfast Thermal, Hydromechanical, and Chemical Well Integrity Simulations for Powering Optimization, Sensitivity, and Risk Analysis. I hope he's going to explain whatever this means. So, without further ado, I'd like to invite Dr. Clement Gilan to join us. I think he already joined us.
Yes, I'm already here. Thanks, Danilo.
Clement is a petroleum geoscience engineer who holds a PhD in numerical modeling of coupled THMC process. His research spans diverse fields, including radioactive waste storage, geothermal drilling, and fault reactivation upon CO2 injection. In 2020, he founded Net2Zero Geosystem, a company focused on developing cutting-edge well integrity simulation tools, collaborating closely with Total Energies. These tools have continuous benefit from their field expertise and experimental data. So the floor is yours, Clement.
Thank you, Danilo, and thanks for the introduction. Also like to thank Pierre-Edouard Vincent for introducing me to SPE Brazil, and I would like to thank SPE Brazil for hosting my talk tonight. So I'm going to talk about THMC, well integrity modeling for risk analysis. So THMC stands for thermal, hydromechanical, and chemical processes. So those are the physics that happens in the subsurface. I'll start first with a short introduction on Net2Zero Geosystems, which is a team based in London. And this team was formed as the result of research and collaboration in Imperial College, and more specifically in the Computational Geoscience Department of Imperial College. And what we focus on is developing numerical simulation tools and services for applications that relate either to oil and gas or the geosystems of the energy transition, such as CO2 storage, radioactive waste storage, gas fuel storage, such as hydrogen or methane. And I would like to start with a little overview of the topics we've worked on previously and how does that builds up to well integrity today. So the first application I would like to talk about is radioactive waste storage. And what you see here is what you call a deposition hole for high-level radioactive waste. Now, this has quite a few similarities with a well, because the radioactive waste that you see here in orange is in a steel casing, and that is then surrounded by what you see in yellow, which is called bentonite, which is a clay-like material that reacts with water, just like the cement. And finally, you have the surrounding rock. So we find casing, cement, and rock in this application as well. And really the key for this application is safety, because you don't want any leakages of radioactive material, because that will remain harmful to humans and the environment for millions of years. So that's why you're looking at thermal, hydromechanical, and chemical processes. And the idea is to look at everything that could potentially happen. And that's not necessarily relevant for oil and gas because the timescales are short, but it's very relevant for CO2 storage when you're going to store CO2 for an unlimited amount of time. So I will just show some simulation snapshot of this application and different processes. So those are the thermal processes. Radioactive waste is hot, so it will stay hot for about 100 years. So this is a 4,000-year simulation. Hydraulic processes, you have here, I talked about bentonite clay. Well, when it's placed, it's dry, and over time, it will suck the water out from the formation. And that's what you see happening here. And finally, this is a little bit more of a close-up. You have the stress. And the stress, which is very important to predict fracturing, debonding, or any opening of fracturing that could lead to radionuclides to leak. So that's it for radioactive waste storage. Now, we've also done some work on fault reactivation related to CO2 storage. Again, we have those thermal, hydromechanical, and chemical processes in CO2 storage and in the application, because you need to monitor the CO2 being injected, cooling down the rock, the the CO2 plume that you have here. So that's hydraulic processes. The heat is thermal processes. And you also have the mechanical process with the activation of the fault. And in this particular case, we looked at how we could stop fault reactivation by producing a little bit of geothermal CO2. And that brings us nicely to well integrity. So what you see here, it's a simulation of shear failure in TotalEnergies experiment. So it's shear failure in the cement. And that's the work we've been involved with for a number of years with TotalEnergies. And I would say that's a research-oriented work where we try to understand how fractures propagate and how wide they open in relation with experiments. But what I will talk about tonight is simulations that are much simpler, much faster, but also much more high level. And we'll see how we can use them for predicting risk. So my talk is going to be about 30 minutes. And after this short introduction, I will clarify what I mean by well integrity, because there's different categories of well integrity, and we are on a particular category. Then I will detail a bit more the physics that are at play when we talk about well integrity. So thermohydromechanical and chemical processes. Then I will focus a little bit on the cement curing process, because it's very important for well integrity. Then I will talk about experiments. Finally, the simulations that we make and how they can be used for risk analysis. So well integrity loss. What we focus on and what we're going to focus on this talk is everything below the surface, and is the permanent structure of the well. So that involves the rock formation, the cement sheath, and the casings. So if I was to take a well cross-section at this level, this is what I will get. You have the casing, the cement, and the rock. And that's a picture I'm going to use a lot in this presentation. So in terms of well integrity loss, we can have debonding. So that is the creation of an opening between the casing and the cement, say, or between the cement and the formation, and that leads to leakage. You obviously have fracturing, different types of fractures, such as shear failure, cracking, tensile cracking in the radial direction, and what you call disking. It's a tensile crack as well, but in the horizontal plane. And finally, you have chemical alterations. So those are microscopic changes in the structure of materials. I could cite casing corrosion is one. CO2 precipitation in the cement is another one. And obviously, those play an important role in well integrity. So those defects are influenced by thermal, hydromechanical, and chemical processes. So I'm going to detail those. I'm going to start with thermal. So that is quite simple. It's just heat transfer, cooling, heating that happens in the well when you produce or inject fluid. Hydrological processes, they're very important in porous materials because you have a pressure there and you might have different phases of fluid. They're important for gas leaks as well. And they can also trigger fracturing and debonding. And then you have the mechanical processes. So that includes the elasticity of a material. If I compress a material, it will deform. If I stop compressing it, it will come back to its original position. This plasticity. So I'm going to illustrate this with the cement, because the cement can have a plastic behavior under certain conditions. So if I was to apply a high pressure inside the casing, then I would compress the cement to a point. And if I was to stop applying that pressure inside the casing, chances are that the cement will have deformed irreversibly and it will not come back to its original position. And there you can see you have a microannuli. So plasticity is a very important aspect of the cement's behavior. Then I will talk also about fatigue, which is the response of a material when you apply a cycle of loads. So if you start injecting CO2, stop injecting CO2, start injecting CO2 over a number of years, the material will experience some fatigue and weaken over time. And finally, we have creep. So creep is relevant for salts or shales because they, under the same load, they will deform at a very slow rate. It is generally a good thing because if you have a shale caprock, for example, it will tend to compress more and more the well over time, closing any gaps between the casing and the cement, for example, and preventing any leaks. So that is generally a good thing. Now there's something else, and that something else is couplings. So relationships between those processes. I'm just going to give you a couple of examples. The first one is pore elasticity. If you have a porous rock with water inside, if you compress it, you're going to increase the pressure. And similarly, if you increase the pressure into a confined piece of porous material, then it's going to expand, and you're going to relieve the stress, some of the stress. So that is the pore elastic coupling is describe the relationship between hydrological processes and mechanical processes. Then there's other very straightforward one, thermal expansion. If I heat up cement or well, it will expand. This also works for the fluid. If I heat up fluid, it will expand. In the case of fluid, we can also talk about pore water freezing. So if you look at CO2 injection, you could have, in certain cases, temperatures down to minus 30 degrees, and that will cause the water to freeze and expand a little bit, which is a very specific behavior, because normally when you cool down something, it tends to shrink, but the water has this specific property that expands when you go below zero. And finally, the chemical processes. So that is a very, very vast, complex class of processes. I'm going to just give a few examples. So casing corrosion is one, CO2 precipitation and the cement is another one. And finally, we have cement curing. So cement curing, I'm going to spend a little bit more time on it because it's quite important. And first, I'll start by telling you why it's important. So this diagram that you have here illustrates the construction of a well section. So you would first start with a borehole. So you have the formation here and your borehole in the middle filled with mud. Then you'll place your casing, and then finally inject your cement in the annulus so that you have cement slurry in the annulus and water inside the casing. And over time, your cement will harden and transform into a pore elastic material. So from a fluid, it will transform into a pore elastic solid. And if you capture this correctly, you will know how much compression there is in your well, how much compression there is inside your cement, and how much compression there is at the interfaces. And that's kind of the starting point of your well integrity simulations. If you don't capture this right, everything that you predict after will be flawed. And so this basically tells you how much more load the cement can take before it fractures or it debonds. So if you're going to make any sort of prediction, cement curing needs to be predicted correctly. So I'll give you some more detail about the cement curing process. So that is a schematic of your slurry. It's composed of water in blue and what you call clinker, which is dry cement particles. And over time, what happens is that water gets consumed, and you have this gray material forming, which is your hardened cement, your product of that chemical reaction. And you have something else as well, which is shown as voids here. So what you see is the structure or the schematic of the structure of the cement. If you will cure the cement at the surface, you don't have those voids created. And that actually relates to cement shrinkage. So this graph shows you the evolution of shrinkage from 0% to about 15% shrinkage after 5,000 hours. And if you look at this into a little bit more detail, you find that this shrinkage comes from the difference in volume between your initial composition and your final composition. So you have the water that's being consumed, you have the clinker that's been transformed into hydrates, which is here. And when you look at this more precisely, you find that your shrinkage is mostly related to the consumption of water by the cement paste. And this reaction is very sensitive to many things, including the depth at which it takes place, the pressure at which it takes place, the temperature, and things like the water to cement ratio. So to illustrate this, if I was to cure the cement in an experiment, which is like a piston, where I would apply a load at the top, this is likely what I would get. You will not have any voids. They will all be compressed, and you will observe significant bulk shrinkage of your cement. So that's for the chemical reaction. Now I'm going to give you some more details about what is the conditions in which the cement cures. So I'm putting again this diagram here, where you have the formation, the cement slurry, the casing, and the water inside. So the formation is subjected to a number of forces, including the overburden stress, which you have here, and then the horizontal stress, which is the tectonic forces. Now the slurry is subject to the weight of the cement slurry column, and that would then apply also on the formation wall and on the casing wall. And finally, you have the hydrostatic pressure of the water, or this might be a different pressure depending on what depth you are at and what the drillers want to do. And so now I'm going to talk about what happens from the moment you start curing. In the previous slide, I told you about water being consumed. Well, that consumption of water leads to a reduction in that PS into that slurry pressure. So essentially, that disappears. And as this disappears, there's nothing to support the casing and the formation. So those forces will push inward. So those blue arrows and those yellow arrows, they will push inward until the cement is strong enough to support them. So you can see here, this is the strength of the cement over time. You start from a fluid, has no strength, and over time it hardens, and as the reaction progresses, it reaches its full strength. So in a little bit more detail, if I was to zoom in into this area here, this is what I would get. You would have the cement structure, the cement slurry, which is between the formation pushing on one side and the casing pushing on the other side. You have on top the weight of the other cement particles, and you have inside your cement, you have your pore pressure, or the pressure of the fluid. And so that disappears over time. And what happens is that the cement gets compressed, shrinks, in other words. And in certain cases, if all the water is consumed, this scenario can also happen. The cement shrinks so much that you have, from cement curing, a microannuli. And things get even worse if you have intrusion of water through those microannuli and the pressure building back up again, because it's going to then increase the size of the microannuli. So this is a very important process to capture correctly. So now, in terms of how does the chemical aspect of cement curing relates to the other processes? So first of all, we talked about the fact that the chemical reaction depends on temperature. So the hotter it is, the faster the chemical reaction. It's also depending on pressure, as we've seen. And now this chemical reaction consumes water. So there's a relationship between the chemical processes and the hydrological processes. So that is that cement pressure drop that we talked about. And we also talk about the fact that the cement was weak at early age and strong at later stages, and that relationship with the mechanical properties on both is that. And finally, we talked about cement shrinkage, and we also have expansion in certain cases when you talk about when you have expensive additives, for example. So I've not given all the couplings that exist and that we use, but I'm pretty sure that you can already see that it's quite a complex model. And this complex model cannot be reliable if it's not validated versus experiment. So that's why we validate all the models that I've presented today versus experiment, and we collaborate with TotalEnergies, Shell, Equinor, and SINTEF, which is a research institute in Norway, which you probably know. And we look specifically at cement curing, debonding, fracturing, leakage rates, fatigue, cycling, and plasticity. So with Total, for example, that's their well integrity experiment test cell. And their focus is CO2 storage. And you can see their setup is quite novel because they have a casing, a cement, which is cured under pressure and temperature conditions, and a piece of rock. Usually, you don't have the piece of rock. So that's quite novel. And what is also novel is that they're able to cool the whole setup to minus 30 degrees to reproduce the effect of CO2 storage, or the possible range of temperatures you could have with CO2 storage. SINTEF in Norway, they're quite focused on pressure and temperature cyclings and leakage. So they have some very good data for that. And finally, Shell, I think the expertise is really on cement curing. Team Voltebig is really an expert in cement curing and has a deep understanding of that. So it's really nice to work with him. So now that I've talked about the physics, the experiments, I can talk about simulations. So I've shown you this diagram before, which is much simpler than the simulations with fracture that I first showed you. This is a simplified well integrity simulation that captures a small section of a well. And the advantage is that it's very fast. A simulation takes about 1 second. So you can see here an example of simulation. And you can see very, very clearly the different behaviors, different 3D behaviors between the formation, the cement, and the casing. Obviously, the deformations have been increased 50 times, so you can see something. Otherwise, the changes are quite subtle. And with this tool, we capture pore elasticity, fatigue, plasticity. We compute the potential for fracturing. We compute damage to materials, and we compute the size of the microannuli when there's debonding. And finally, we compute the leakage rates. And because we have a small section of a well, the way we use it is by dividing the well into a number of sections and performing simulations for each section. So as an example, section A will have 5 different materials. So formation, cement, casing. Section B has a plug, so it's 4 material. And section C is a little bit simpler, it's only 3 materials. And how do we make now a well integrity risk assessment based on this? Well, we look at the life of the well, and we make simulation for each stages of the life of the well. So we start with the construction of the well, with the curing of the cement, some pressure testing, and then we move on to production cycles, CO2 injection cycles, workovers, and finally plug-in and abandonment. And I'm going to give you a little graph to illustrate what a simulation is, just as an illustration on an actual simulation. So in X, you have the time. So you will have here about a month. Here is 1 year, and this is 10 years. And this illustrates the potential for failure. So the higher it is, the more potential for failure there is. The lower it is, the less potential for failure. And this is a well failure line, meaning then once the green curve crosses the black line, you have failure. And what I've done here is only one well integrity simulation based on one set of inputs. Obviously, we need to consider uncertainties because pretty much everything about the well has uncertainties. So the pressure and temperature conditions at depth, but also of production, the cement curing conditions, and the properties of formation. So those are just examples, but there's more. So if I was to consider an uncertainty and let's say change all parameters by 20%, well, I might have a very different simulation as a result. And this second simulation, you can see here has lots of failure. You predict a lot of failure with that simulation. So we don't do one simulation, we don't do two simulations, we do thousands of simulations. And that is helped with the fact that we have very short simulation run times, so about 1 second. Plus we run on a cloud services, so we can perform tens of thousands of simulation in a very short time. And what we do with those simulations is what you call Monte Carlo simulations. So within a certain range of input parameters, you choose and you perform random simulations by choosing different parameters within that uncertainty range. And that gives you a probabilistic distribution for the failure of the well. So regarding the bonding, fracturing, leakage rates. And I'm going to illustrate this, this uncertainty, this probabilistic distribution by a gradient. So now you'd have to consider that the green line at the bottom is your best case scenario. The red line is your worst case scenario. And the gradient in between is all the distribution of all the potential cases. And what illustrates the uncertainty is this distance between the best case scenario and the worst case scenario. So the wider it is, the more uncertainty you have. The narrower it is, the less uncertainty you have. So now I'm going to move on and how give you a couple of examples where this approach can be used. And the first scenario that I'm going to put forward is a very fortunate scenario where you have an extensive data set for a specific well. Everything is well characterized so that there is a very small uncertainty on the data. So in return, you can have quite a clear prediction. So this is an example of a simulation which you can have with a well-defined data set. And you can see that the distance between the best case scenario and the worst case scenario is quite small. So that means we're quite confident in that prediction. So in this case, this is a good one, but it could also be a bad one. And if it's a bad one, then you probably want to stay away from that well. But so that is kind of the nicely behaved scenario. There's another scenario where you might have limited data on a well, and you may be even looking to make a decision on about 100 abandoned wells, and you're looking at 10 different potential locations for a CO2 storage project, and we want to know which one has the best wells. And the wells say they were abandoned about 30 years ago, and the only thing you know about them is their structure and the type of formation the well is traversing. So in that case, you can still do an assessment, but you need to consider a high uncertainty. And so that means you have a much thicker curve now, and this is a potential output which you could get. And you can see here, even though I've considered a large uncertainty, it looks like I've got failure every time for every possible scenario, pretty much every possible scenario. So you probably want to stay away from that well. It's not the well you're going to be looking at first. There's a second outcome where even though you've considered a large uncertainty, it seems that you're far away from failure regardless. So that's a really positive prediction, I would say. And then there's a third outcome, which is where the simulation doesn't tell you much because you have such a high uncertainty, and it could be very bad or it could also be very good. So in that case, typically what you would do is ask an expert to provide some guidance and to reduce the uncertainty on some parameters. And you could also do some more data acquisition and get some key data that would reduce the uncertainty and basically put you in a better place, so that you then fall into either of those cases, either a favorable prediction with a low uncertainty, or an unfavorable prediction but with a low uncertainty as well. And to finish, I'm going to finish on the third type of scenario, which is new wells. So for new wells, we're working on something different, which is about optimization. So we try to optimize well designs and well materials, so they are more safe and less costly. So to understand optimization, I first need to tell you about what a standard simulation is before I tell you what an optimization simulation is. So with standard simulations, you start with a set of inputs, then you pass them to your simulator, to your well-integrated simulator, and that gives you a result. That's quite simple. But for a optimization simulation, you go the other way around. You start with the result, and you choose the result. So that could be you want minimal debonding, minimal fracturing, you want a minimal leakage rate, and you could also have a minimal cost if you have data relevant to cost and relevant to well integrity. And then you're going to perform a lot of simulations with a lot of different parameters. And optimization methods are going to give you the best input that gives you the less debonding, the less leakage, and the less cost. And as a result, you will get the ideal cement compositions for this, the ideal well geometries, and even the ideal pressure and temperature load cycles. So we see an interest here for, in particular for CO2 storage, when you want to design CO2 injection cycles and temperature so that your well is going to be able to support 20 years of injection with something like 200 injection cycles. And that's it. That finishes my presentation. I hope everything was clear. And I hope that wasn't too much information. If you have any questions, I'd be happy to hear them.
Okay, come on. Thank you very much for the presentation. Well done. Very interesting topic, and you made it easy for us. Yeah, so Pierre could not be with us tonight, unfortunately, but he saw your slides and left me a few questions. So I'm going to start with one of his questions. On slide 4, if maybe you could go there, you are showing cement sheet failure, shear stress cracks from research done for Total Energies.
Is it this one?
No, 4.
4. Because I think it's probably changed a little. Yeah, 4. Okay.
Okay. And the curiosity of PI is the actual consequences of the failures. Once they have formed, cement has failed, cracks have developed. Would those under stress provide sufficient conduit for leaks? And can we do something if they do? He's talking about the curative mode. And if we believe there might be leaks, can we estimate their severity? I think he's trying to quantify the leakage. So that's the question.
Yeah, so I think I'd like to show you this slide. And Pierre asked about fracturing, and not all fractures matter for leakage. For example, shear failure is that type of failure, so everything stays in contact. So this tends to have a low leakage rate. Disking is tensile failure, so it's a little bit more of an opening, but because of the orientation, because it's across and not along the well, this tends on its own. This doesn't do any leakage. But on the opposite, radial cracking, which is fractures in the longitudinal direction, that creates leakage pathways. And plus, it's a tensile failure. That means there's a much larger opening. And I would say yes, this can be predicted versus experiment. That's That's what Syntef has been working a lot on, calculating the leakage rate of CO2 or any gas in the fracture. And especially they've been looking at the fact that the fracture might be saturated with water. So therefore you need a certain capillary pressure of the CO2 or of the gas to displace that water and be able to create a leak. And that is very reliable predictions we can make of those type of phenomena.
Yeah, thank you for your answer. And a doubt of my own. The simulations are done in the design phase of the well, but you have some, what I understand, but you have some process to update the analysis based on real monitoring of the well or something. I don't know if it's possible to keep running and updating the simulations during the operational phase of the well.
We can history match our predictions with something like a cement bond log. But the reality is, once you build the well, it's really difficult to get data across the casing. And it's quite difficult. So there's not much direct measurements we can use after the well's been built. We can use all the data, all the logging that was done before the well has been built. Of course, today the technology is getting better. There's also sometimes sensors inside the cement that are placed there and left during the curing, and then you can come and collect data from them after you've started operating your well. So that could be a potential, but today, to be honest, it's quite difficult to have information about the state of the cement.
Yeah, you are absolutely right. We are making a lot of investments trying to put sensors in the outer casings and even in the cement sheets. But I was wondering, maybe inference, looking for other indirect variables, but I understand that the difficulties of that. Luis Lopez from the audience is thank you for the presentation on risk assessment in the cement process in wells. And he has a question about what are the conditions for good cement curing in well? It's a more generic question, but I think you can.
It's a difficult question to answer especially because the validation we do in the calibration of the model is not complete. So I'm careful. We have a model that predicts everything, but we're finishing the validation. So what I will say is that pressure and depth is important for the cement, because you have the more pressure you have, the more pressure drop you have as well. So I was talking about a pressure drop. If I go back to the slide. This slide here, this drop will make the cement compress. You will compress the cement more because of that pressure drop, and likely you have a better bond at greater depth. And obviously, there's the most straightforward conditions, which is the cement still has a high water content, and not all the water is lost to the formation, meaning that the cement can't hydrate properly, and then it has no strength.
Okay, it makes sense. And he has another question about the Driscoll simulator. The question is, does the Driscoll simulator also calculates the microannulus in the cementation process?
Yes, it does.
Okay.
Yeah, it does. And that can happen during the cementation process for sure, especially if you have a microannuli, and then there'll be more water coming into it, which is good for the cement hydration reaction, but is also bad because of that effect that we've seen, where pressure pushes on the walls of the casing and of the formation, especially if the formation is not porous, and that increase the microannuli.
Yeah, thank you. And now it's not actually a question, but just a curiosity. You mentioned a broadly range of applications of the simulations. And thinking about my own interest here as an engineer who works with well integrity in subsea wells here in Brazil, have you any thoughts about simulations in the pre-salt scenario? We know that the pre-salt scenario poses additional challenges in the well construction due to the mechanical loads from the salt layer and also the cementation issues that can arise from the cement operations with fluid losses. So I don't know if you have any thought about, or if you think it's you can have some insights from the simulator that could help
Yes.
us.
So I think if you talk about salt, you have to talk about creep. And we're currently developing a model for creep to capture the slow movement, the slow compression of the salt. Then the water loss to the formation, that's something we already capture, and we see is quite important. And finally, for basalt, I'm not quite sure what you're referring to when you talk about basalt. What is complicated about basalt?
No, you don't have basalt problems. I'm talking about when you perform the cementation of displacement, we have problems with fluid losses.
Yeah.
I don't know if your model can simulate the impact of these fluid losses in the.
Yeah, you can do that. Yeah. And really, what's going to happen is that the cement reaction is not going to be complete, and you're going to have a very weak cement.
Okay, so I think we can have advantages by using these tools in our scenario here in Brazil, especially talking about pre-salt scenario. So very interesting. I have a lot of other questions that we can talk later. From the audience, we have covered. I think I have covered all questions. So I'd like to thank you again, Clement, for the presentation and for your time. And thank you Amanda and the guys who organized this amazing section. So thank you very much and have a good evening.
Thank you everyone for hosting me. Have a good evening.
Bye-bye.
Bye-bye.
Thank you.